things will be a little bit more low level. Let's see. Okay, I think everything should be fine now with the slides. So, okay, slideshow. All right, we're talking now about the basics of natural language processing. We all know ChatGPT, we have all interacted with it. You know that if you go and ask it what is 2 plus 5, it will tell you the correct answer. Since ChatGPT is a proprietary model, we don't really know exactly how it works, but we have good reason to believe that, and actually in a technical report that they did reveal certain details about the model, we know that at the very core of this model lies a language model. At the very core of this AI agent lies a language model. And what a language model is basically something that, you know, on the forefront, we see this dialogue-like user interface. But what's happening in the back is that there is this model that basically gets an input that might be formatted something like user says, what is 2 plus 5, agent, and then from this input, the model has to generate the next token. Or rather, it has to generate the full string that we see as an answer. But effectively, what it's doing is it's generating one word at a time. So given our question, it might start by generating the word 2, and then generate plus, and then generate 5, and then generate equals, and finally, the key answer here, the word 7. So language modeling is all about predicting the next word in a sequence of words. Formally, what we're looking for when we want the language model to predict the word 7 is a probability for the word 7 out of a list of all the possible words the language model can predict, conditioned on this past context, which is the conversation that has happened so far. And if we assign this probability to P of 7, then we basically want a language model that for this specific context will give us P of 7 that is higher compared to the probability it would assign to the word 8, that is higher than the probability it would assign to the word 20, that is much higher than the probability that it would assign to the word egg, that is completely irrelevant in this context. So let's dive a little bit deeper into what's actually happening here. So on the one hand, we have the input, which is the past text, the dialogue that has happened so far. And we have the output, in this case, the word 7. And in between these two, we have a language model, which basically maps from input to output. That model between input and output is a complex function, usually based on a neural network, which is basically a series of computations which map an input into an output. But because these have to be and just to translate things into some of the terms that you've heard already, and to be sure that there's a clear understanding of what I mean by model and weights, if we take as an example a very simple task we have to solve where we find that the weight and gender are determining factors in what is the optimal dose of a medication for a given disease, we might find that the model is such that the dose for men should be half their weight plus 80, the dose for women should be half their weight plus 50. So how we might formalize that is to represent the input features as the age of the person and then a one-hot representation of the gender. What I mean by one-hot is we have these two genders, male and female. These genders are categorical variables, they're non-numeric, but we want to perform some computations with them. In machine learning, we're always performing computations, so we have to have some numeric way to represent them. If we just translate them into arbitrary numbers, that's not going to be very useful for the purposes of computations because these numbers will not really be meaningfully representing the values of the variables. So we might opt for representing them as what is known as a one-hot vector, where we basically take all of the categorical variables that we have, in this case, 2. So can we create this vector of zeros, mostly, of the size of the number of categorical variables, in this case, 2, and we assign a 1 for the relevant value of the categorical variable. So this is just to say that we might represent male as 1, 0, and female as 0, 1. And then that allows us to build a weight matrix, which we can directly take the dot product of with the input vector and get the correct output. And this weight matrix is just a visual representation here of what Dr. Maxim introduced as the weights W here, for 1 for each value in our input feature vectors. So having established that, let's see what that looks like for language modeling. So the problem with language, the difficulty, is that words are discrete units. Again, similarly to how male-female is a categorical variable with no natural numeric representation, words are categorical variables that we have to find a way to translate into numbers before we can feed them into any kind of machine learning model. So again, if we were to go about that in the most naive way possible, we might say, okay, we're going to assign the word user value 1, the word what value 2, the word is value 3, and so on. The problem with that is that these numbers are not meaningful in any way. And so any computations that we try to perform over them will be extra hard because we have to account for the fact that these words are represented by arbitrary numbers. So what we might do instead, similarly to before, is use a one-hot vector. So let's say in this example that our whole vocabulary, all the words that we want to build a model for are the ones present here. There's I believe 12 unique words. So we have a vector of 12 slots. A vector is just an array of numbers. So we're building this vector of dimensionality 12, and we're saying when we want to represent user, we're going to put a 1 in the very first position in this vector, and all the rest will be zeros. When we want to represent what, we're going to put a 1 in the second position in this vector, all the rest will be zeros, and so on. So this now allows us to represent words in a slightly less confusing way from the perspective of the model, but still in an arbitrary way. Still, we have these very many zeros in the vector that don't really serve us any purpose. We have this fairly long vector to represent just a small set of words, and still the representations are arbitrary. So what we can do instead is to use, instead of sparse meaningless vectors, to use dense meaningful ones. And how we're going to go about building these dense meaningful vectors is by following the observation made by Firth in 1957 that you shall know a word by the company that it keeps. What that means is, if we look at the text we have here and generally think about what we know about language, the word equals would often appear in the same sentence as the word plus and vice versa, because these are both mathematical terms. The word plus would also often appear between two numbers. Words for numbers would often co-occur together because we might want to express something like the year 1993, or we might want to say 2.7, and so on. So numbers often co-occur together. And then we can also say the word what is often followed by the word is, because this is often how a question is formed. So all of these observations are things we know as language users, but we don't actually have to manually describe them. What we can do instead is we can build dense vectors based on counts. So we can say, given a very, very small corpus, we would call it, which is just a collection of text, we can take every word from this corpus and put it in a matrix like this of n by n words that are all the words found in our corpus, and then we can just count. whenever I see the word 3, would I see another occurrence of the word 3? In our corpus here, we don't see that, so we put a 0. Same for glass, but then we go to doctor. In this sentence here, we see the word 3 right here and the word doctor here, so we will put a 1. Similarly for plus, we see 3 plus 8 equals 11, so we would say, I've seen an occurrence of the word 3 in the context of the word plus. We can do that again for the word the and so on, and then for the rest of the words in our corpus, and we obtain this matrix, which now we can interpret as each row of it. So the horizontal set of cells associated with the word 3, for example, can now be interpreted as a vector representation of the word 3, which is dense in the sense that few cells will be zeros, and it is meaningful in the sense that the vector that we build in this way for the word 3 will likely be somewhat similar to the vector that we built for the word 7, that we built for the word 11, because you can imagine a lot of contexts in which these words will occur in similar positions surrounded by similar words. So for example, all of them might have a high value for co-occurrences with the word plus, because all of them are likely to often co-occur with the word plus. Of course, this has to be derived from a much, much larger corpus of text. And as we will discuss later, in practice, we do learn representations from huge amounts of text, because that is when they are most accurate. Now, one problem remaining here is that these vectors are still going to be the full size, the full dimension, their dimensionality is going to be based on the full size of the vocabulary that we extract from the corpus. Again, by vocabulary, I just mean the number of unique words that we encounter in a large volume of text. So if you think about the English language, different claims have been made about how many words actually exist in it, but let's say it's 1 million. This means that if we take a big enough corpus of English, we extract the vocabulary from it, and we learn vectors in this way, we will be learning vectors of dimensionality 1 million. And if you think back to what was discussed before about how we build neural networks, how we build machine learning models in general, for every feature in our input representation, we have to have some sort of a weight that's going to allow us to determine how much that feature contributes to the final output, which means that for a vector with 1 million features, we will need to be learning 1 million weights. And then it gets very, very computationally heavy as soon as we start learning these weights with gradient descent. But even just storing these vectors, like imagine having to store 1 million vectors of size 1 million on your computer. That's a lot of gigabytes. So we don't want to do that. We don't want to learn these huge, huge representations and models. What we might do instead is, once we have computed these count-based vectors, we could use a dimensionality reduction technique. I know we haven't gone into depth about what that is, but I'm just telling you these exist. You can, in theory, compress this vector into a lower dimensionality, which will be more manageable. And people have, maybe 10 years ago, tried to do that, found that at the time it worked all right, but actually what we've learned since then is that there's many better ways to go about learning the representations of words. So, I will now talk about word2vec, in case you've heard about that. This is a way to initialize dense low-dimensional vector representation of words randomly and learn them algorithmically through gradient descent. So this is what our embedding matrix would look like. The size of it is V by D, where V is the size of the vocabulary that we've extracted from our text corpus, and D is just a dimensionality that we choose as appropriate for our word vectors. So this could be 100, it could be 300, it could be 1,000, depending on how much data we have to learn from, how much compute we have available, how complex the task is that we want to solve, and so on. In the peak of word2vec, the typical dimensionality of this was 300. The way we go about learning this, or one of the ways that I will cover today, is continuous bag of words algorithm. The training objective here is, given the vectors of surrounding words, we want to predict the target word. So what this looks like, if you look at the training samples down here, is given the words +8 = 11, we would want our model to predict that the word 3 is a likely word to appear in this context. And in this specific algorithm, the context is actually treated as a bag of words, which is to say that the order doesn't matter, which is why I'm representing the context as a set here. Just to say that the word can appear anywhere in this context, and this is what the algorithm is trying to learn. As you can imagine, this is not optimal, and we will see in a little while how it can be improved. But in 2012, 2013, this proved to be an extremely effective way for representing words for the purposes of natural language processing. So how we would go about computing the mapping from input to output is we would take the vectors for the context words from our embedding matrix. In this case, the example is 3 + 8 = 11, that gets mapped into equals. So we will take the vector of 3 + 8 and 11, and we will actually simply sum them. And what that the implications of that is, again, that the word order doesn't matter, because summation is a function that loses that information. So we just have now this one vector of size 1 by d, which represents the whole context. And we will then take the dot product of this vector with what is called an unembedding matrix, which is has the same dimensionality as the embedding matrix, but it's transposed. And by taking the dot product of these two things, the vector and the matrix, we get finally one vector, which has size v and represents the predicted distribution over the vocabulary. So the first cell in this vector might represent the probability of the word 3 occurring in the context that we've provided. The second would represent the probability of the word glass. The third would represent the probability of the word doctor. And finally, the probability of the word equals would be represented by this cell here that I have intentionally made darker than the rest, with the goal of, with the idea of the intensity of the color representing the probability mass assigned to that token. So since here we want the model to predict equals, we would hope that this specific cell in the vector has the highest value. Because finally, how we would make a prediction is by taking the token with the highest probability from this whole vector. And how we would train the model is we would take this vector, the one to the left here is the output of the computations shown on the previous slide. And the one on the right is the target distribution. This one is just a one-hot vector, which has zeros in every other cell except for the one that represents the word that we want, the target word, the one that we want to be predicted. And by computing the cross entropy between these two, we obtain a loss that we can use to then compute the gradients with which we have to update the embedding and unembedding matrices. The product of this operation is that we have these word embeddings, which are low dimensional, dense, and meaningful, and represent the distribution of words in context. If we imagine a very simplified case where we only train word embeddings with dimensionality 2, which means that we can plot them in a two-dimensional space, we might hope to obtain word embeddings that look something like this, where the words for bus and car are very close to each other because of how highly related these two concepts are semantically. Bicycle is somewhere nearby because it is still a vehicle, but a little bit different. It's not motorized. Then over here, we might have some furniture. And in between the two sets, we might have the word seat, which sort of has something to do with bicycle, car, but also with chair. So this is the goal in the end, is to have an embedding space in which words are represented in a meaningful way with respect to one another. And this is learned from the context in which they occur. Words that occur in more similar contexts will end up having more similar representations, and words that occur in very different contexts will end up being quite far apart in this, low dimensional from the perspective of what we talked about before, but still high dimensional from the perspective of, here we only have 2 dimensions. Usually we're working with upwards of 300. Once we have these word embeddings, there's a lot of things we can do with them. One thing is we can solve sequence classification tasks. So Dr. Maxime covered those a little bit. Now I will go in a bit more detail. In sequence classification, the input is a piece of text and the output is a label that classifies the text according to our needs. So one example is sentiment analysis, where we might have some comments users left on a web page, for example, and we might want to classify them automatically into negative, positive, or neutral. The way we would go about that is we would want to have a representation of the input text and this matrix W, which has the dimensionality of the input text representation on one hand, and on the other, the dimensionality of the classes that we're working with. So here W would be a D/3 matrix because our input is in the dimension, has D dimensions, and there are 3 possible labels we want to predict: negative, positive, or neutral. And by taking the dot product of these 2 objects, we'll again obtain a vector of dimensionality 3, where each cell, each of the 3 cells represents the probability of class negative, positive, or neutral. That's just the classic linear classifier. And how we will actually obtain the representation of text can be very simplistic. Again, we can assume word order is irrelevant. For sentiment analysis, it often actually is, because as long as we're representing that the text contains the words "this movie" and "sucks," this final representation here that can be just the sum of these 3 vectors is going to contain the negative sentiment of the input text. So hopefully the matrix W will accurately reflect that by resulting in a high probability for the negative class. Another task that we can solve, and that is very common in natural language processing, is sequence labeling. Once we can represent words in text, we can perform sequence labeling where the input is a sequence of words and the output is a sequence of labels, 1 for every word. A very classical sequence labeling task is part of speech tagging, where we have input text like "I like the music," and the corresponding label sequence would be pronoun, verb, determiner, noun, which are the parts of speech of the 4 words in the input. Again, the way we go about this is we have a weight matrix that we want to learn, W, which has dimensionality D/N. N is the number of parts of speech that we might want to predict. And we will be taking the dot product of our input representation with this matrix. In a somewhat naive approach to the task, we can treat each word as a separate input and actually say, okay, first I'm going to classify the word "like." So I'll take the embedding of this word, I will multiply this embedding with the weights matrix, and I will get a prediction for the word "like." Then I'm going to take the embedding of the word "movie," and I will repeat these steps to get a label for the word "movie," and so on. The problem with this, however, is that, as you might already be thinking, some words actually have different parts of speech depending on the context, such as the example here, where "I like the music" is a sentence where "like" serves as a verb, but in the sentence "it looks like a toy," "like" actually serves as a preposition. If we take this naive approach of classifying every word separately with by disregarding the context, we will always be making a mistake on at least one of these 2, right? We will either, our weight matrix will either predict verb or preposition for every occurrence of the word "like" in our data. So how do we go about solving this? Well, in come contextualized word embeddings. If you have heard about BERT or masked language modeling, this is what I'm talking about here. So these are word embeddings quite similar to what we were looking at before, but now order matters. Because of course in language order is very important and we lose a lot by disregarding it. So having the same training corpus as before, what we're now doing is we're taking training samples, we're creating training samples by masking some part of the text, feeding the masked text as input to the model, and trying to predict what has been masked. So previously, we would have taken +8 = 11 as an unordered set of context words and tried to predict 3, whereas now we're taking it as a ordered string, and we are masking the word 3 and trying to predict it. We cannot do this just with an embedding matrix. We actually need a second set of parameters, which will update the word embeddings with information about the surrounding context. So the word embeddings that we talked about before, the basic ones, they're trained to learn about the general context of words. They're trained to tell us what company words tend to keep, but that is based on an entire corpus. Now we're taking these and we're actually further contextualizing them with the specific context in which they occur in the instance that we are looking at. And the way we go about that is we use an additional set of parameters called an encoder, which is a system of many W matrices. You can think of it just this way, that each take an input and produce an output. And in the simplest case, both input and output have D dimensions. We can just stick to that for now. So how this actually goes is for an input like 3 + 8 mask 11, where we want to predict the mask token equals, we will be passing to the encoder the word embeddings of 3 + 8 and 11, and also a special word embedding for the token mask. And this encoder will contextualize these embeddings with respect to one another. And actually next week, you will learn what is the most common architecture used these days for that and how that works exactly. For now, I will just leave that as a black box and talk about the output of this encoder, which is a set of contextualized word embeddings. So each of these now represents the original word with its semantics derived from the full text corpus, but also with contextualization with respect to the exact sentence in which we're observing it here. So the first contextualized word embedding here would be for the word 3 in the context of +8 mask 11. And the way this model is actually trained is by taking now the representation of the mask token, the contextualized mask embedding, multiplying it again with an unembedding matrix to obtain a probability distribution over the vocabulary, and similarly to before, comparing this probability distribution to the target distribution, which is a one-hot vector where all other words are 0, all values for other words are zeros, and the value for the word equals is 1, taking the cross entropy between these two to obtain a loss signal, and using stochastic gradient descent to backpropagate this loss through all parameters in the model, most importantly, through the encoder and the embedding matrix. So coming back to sequence classification again, let's see how we can do that better with contextualized word embeddings. If we take again the example, this movie sucks, and the desired label is negative, we can now again take the sum of the word embeddings for each word in the input, but by doing that, we're not actually losing information about the word order, because each word embedding is now contextualized with respect to the full sentence, so it carries information about the word order. And there are actually much more elaborate ways in which this can be done, but I just wanted to keep it simple for now and tell you that this is a perfectly reasonable thing to do if you want to perform sequence classification. And coming back to sequence labeling, where we had this problem with the word like, we're now not going to run into this problem, even if we stick to the simple approach of classifying each word independently, because the representation of like here on the left side is not going to be the same as the representation of like on the right side. They will be similar because the underlying word embeddings that we're passing to the encoder carry information about, carry conflated information about the occurrence of these words in the full text corpus, but they will be different because one is observed in the context of I like the music, and the other one is observed in the context of it looks like a toy, and this information is now embedded inside of the contextualized representation of the word. And we've made our way back to language modeling, which is where we started. So how do we go about predicting the word 11 from 3 plus 8 equals? Well, we can conceptualize this similarly to how contextualized word embeddings are trained. You can almost imagine that we solve the same objective as in contextualized word embedding training, but we always put the mask token at the end of the sequence. So we can have 3 plus 8 equals mask. The mask occurs in the position of the next token, which is what we want to predict. And we can just do the same as before to obtain a probability over the vocabulary and to get a maximum over that, giving us the word 11. In practice, we find that we don't even need this mask token. We can directly take the representation of the last token of the sequence, in this case equals, and we can take the dot product of that with the unembedding matrix. So remember that in both of these cases, this last arrow here is a simplification for, where do we have that step? Yes, for this step here, where we multiply a vector with an unembedding matrix to get that vocabulary distribution. But we don't, like I said, we don't need the mask. We can directly do that from the last token in the sequence and train a model again with cross entropy, where this vector has to be as similar as possible to the one hot vector representing the target. And we find that this system is flexible enough to learn good representations of the input that allow it to correctly predict the next token. And the way we would go about predicting yet the next token is by feeding back in what the model predicted on the previous step. So we started off with 3 plus 8 equals. We predicted 11 here. And now we're feeding 11 back into the language model, getting a representation for this now new last sequence token. And we're using that one to predict the next new token, which is a full stop, which will then in turn feed back into the model if we want to continue predicting tokens. So this is everything that I wanted to cover today. Just a couple of last notes about some practicalities around the vocabulary, some things that, simplifications I didn't mention so far, but are worth being aware of. So we usually learn word embeddings and language models from huge volumes of text. As I mentioned, these can go up to 2 billion or sometimes even trillions of words, which means that the unique number of words in this corpora is going to be huge. So even if we're in this lower dimensionality, before I was talking about account-based embedding matrix, account-based word vector matrix of 1 million by 1 million, we have now reduced the dimensionality to an arbitrary value d that we can set to, like I said, 300, for example. But still, if our vocabulary has 1 million words in it, we will be storing and learning this huge matrix of 1 million by 300. It's too much, it's not practical. So we have to make certain adjustment. One common thing that is widely done for language model training these days, or any kind of natural language processing, is instead of using whole words, we split words up into subword tokens or subword units. And this ends up reducing the size of our vocabulary because there are often shared subword tokens between different words. So, this is a completely random split I've made here, but you can imagine that this THR here, from tree could be reused when we're looking at the word throne, could be reused when we're processing the word triathlon, I guess, and so on. Similarly, for each of these tokens, there's, we are basically compressing. This is actually called byte-pair encoding. It's a compression algorithm that reduces the vocabulary that we have to work with. And now each of these subword units is represented by a vector. And it's a little bit harder at first to see why these vectors should still be meaningful when they're representing somewhat arbitrary subword units. But where the power comes from is actually that encoder that is going to take the seemingly meaningless units, take the vectors that we've learned for them, and compose them into meaningful representations for the words underneath. I'm busy. So the next thing I want to mention is that still, even with this technique, we might end up learning quite a large vocabulary. And what we would want to do in that case is to disregard very infrequent tokens. We might set a threshold of a minimum of 5 occurrences, for example, for a token to end up in our vocabulary. We would also often introduce an UNC token, standing for unknown token, to cover any tokens in the input that is not in the vocabulary. So even learning a vocabulary from such a huge amount of text, there might always appear a new word that we want to be able to process. And in that case, we might just represent it with this special UNC token and the corresponding embedding that we've learned for it in order to be able to, in some form, pass it as input to our model. And lastly, we introduced a beginning of sequence token to allow models to predict text from an empty sequence. So if we want to just start predicting from scratch, from nothing, we can use this beginning to sequence token as the first input to the model from which it will start predicting the next tokens. And we also introduced an end of sequence token to allow models to learn when to stop predicting tokens. Because if you think about it, ChatGPT somehow knows when it's done generating text, when it's done predicting new tokens, and it has completed the answer to your question. Okay, so with respect to NLP, today we covered word embeddings, sequence classification, sequence labeling, encoders, contextualized word embeddings, and language modeling. Next week, you will learn about transformers, which is the architecture behind the encoder and the language model. You'll learn about encoder decoders and about parameter efficient training. And if you feel that there's anything I discussed today that you would like to get a better overview of, please comment on YouTube. We can try to include it in next week's lecture as well, if time permits. Thank you very much for the attention. Laura Rossi, should we take some questions? Technically, we are now at the end of this session, but if you're able to stick around for a couple more minutes, I'm happy to answer questions.
The last question so far regarded the schedule, and I think you just covered it. You just answered that next week there will be new things, so please join us next week.
Yes. So next week we will have 1 lecture on NLP and 2 lectures on computer vision, as well as a lecture on coding for NLP, where we will talk about general advice for coding, debugging, common frameworks for deep learning, and others. Okay, while we wait for any questions, I just want to leave with one closing remark, which is this Olympiad is a new event. It's a very timely event with how much AI has grown in popularity and the need for even the youngest among us to be aware of how it works, where it fails, what the role of AI is going to be in our future. But this is the first year that we're doing it. We're putting a lot of effort and passion into designing the problems, in organizing the on-site event and everything. If you have suggestions for, things that you think would work well, please share them with us constructively. And if you find that, we make a mistake here and there, also forgive us, because it's the first time that we're doing this. I'm sure that for next year, a lot of things will be more polished, but we still believe that we will have a great event in Bulgaria in August. We look forward to seeing you all there. I will not be here next week for the webinar, but other colleagues will be giving lectures again on NLP, CV, and coding for ML. I don't see any other questions on YouTube, so I guess we can wrap it up.